U.S. Physics Olympiad Year 2025 F = MA. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is discount for group classes. Message me if interested. My email is fred1996@hotmail.com. Solutions for all problems can be found at the link in the description under this video. Problem number 1. A particle is moving on a plane at a constant speed of 1 meter per second, but not necessarily in a straight line. Which of the following plot pairs could describe the particle's position over time, in rectilinear coordinates? Solution for problem number 1. All three plots describe the particle moving at a constant speed. In plot 1, the particle is moving in a circle of radius 10 meters, and traversing the full circle in 10 seconds, so its speed is approximately 6.3 meters per second. In plot 2, the particle moves at a constant speed of square root from 0.8 square plus 0.6 square, which is 1 meter per second. In plot 3, the particle moves at a constant speed of square root from 0.5 square plus negative 0.5 square, which is less than 1 meter per second. So the answer is B. That was solution for problem 1. Problem number 2 and 3. The following information applies to problems 2 and 3. 3 identical disks are placed on a frictionless table. Initially, 2 of the disks are at rest and in contact with each other. The third disk is launched with speed v directly toward the midpoint of the 2 stationary disks along a path perpendicular to the line connecting their centers, as shown in the diagram. Analyze the motion of the disks after the collision, assuming all interactions are perfectly elastic and that when the disks collide, there is no friction or inelastic energy loss. Problem 2. Assume that all 3 disks collide simultaneously. What is the final velocity of the third disk? Solution for problem number 2. By symmetry, the third disk continues to move along the same axis. The first 2 disks experience only a normal force from the third disk, which is at an angle 30 degrees to the third disk's original velocity. Thus, if the third disk has final velocity vf, and the other 2 disks have final speed u, conservation of energy gives v square equal vf square plus 2u square. And conservation of momentum gives v equal vf plus square root 3u. Solving the system gives vf equal negative v over 5 and u equal 2 root 3 over 5v. This is the answer D. And that was solution for problem 2. Problem number 3. Assume that there is a little imperfection in disk's initial alignment, so when the disks collide 2 collisions happen one at a time, rather than all 3 disks colliding simultaneously. What is the final speed of the third disk? Solution for problem number 3. After the first collision, the disk that was at rest gains speed v1 equal v cosine 30 degrees and the third disk has speed v3 equal v sine 30 degrees, in the direction that's perpendicular to the line between the disk centers. The component of the first disk's velocity along the line connecting their centers is transferred to the second disk. The perpendicular component is unaffected. The third disk is now moving in a direction that's 60 degrees off from the line connecting its center with the center of the disk that's still at rest, second disk, so after the second collision, disk that was at rest will gain speed of v cosine 30 degrees sine 30 degrees and the third disk will have speed v3 equal v sine square 30 degrees, which is v over 4. This is answer 3 and that was solution for problem number 3. Problem number 4. A mouse M is running from A to a prime with constant speed u1. A cat C is chasing the mouse with constant speed u2 and direction always toward the mouse. At a certain time MC perpendicular to AA prime and the length of MC equal L. What is the magnitude of the acceleration of the cat C? Solution for problem number 4. For small angles delta theta we have next diagram. On this diagram acceleration A equal delta u over delta t. But delta u equal u2 delta theta. And delta theta over delta t is angular speed omega of point M around point C, which is just u1 over big L. Finally we have acceleration A equal u2 u1 over L, which is answer C. That was solution for problem 4. Problem number 5. 3 identical cylinders are used in this setup. 2 of them are placed side by side on a horizontal surface, with a negligible distance between their surfaces so they do not touch. The third identical cylinder is placed on top of the first 2, such that their centers form an equilateral triangle, as shown in the figure below. The coefficients of friction are μ1, the coefficient of friction between the cylinders, and μ2, the coefficient of friction between the cylinders and the ground. For which of the following pairs, μ1, μ2, will the system remain in equilibrium? Solution for problem number 5. From the force analysis diagrams and symmetry, we get a system of 4 equations in order to balance all forces and torques. There is normal force N1 between cylinders and normal force N2 between cylinders and the ground. There is force of friction F1 between cylinders and force of friction F2 between cylinders and the ground. The first equation we can get from total weight acting on cylinders from the ground. The second equation we can get from the projection of force of friction F1 and normal force N1 on the vertical axis. The third equation is projection of friction forces F1, F2, and normal force N1 on the horizontal axis. The equation 4 we will get from total torques acting on the cylinders from friction forces F1 and F2. Solving this system we will get results for all 4 unknowns. Requiring F1 less or equal μ1 N1 and F2 less or equal μ2 N2 implies conditions for μ1 and μ2. μ1 is good for pairs 1 and 2. μ2 is good for pairs 2 and 3. So the correct answer pair 2, which is answer B. That was solution for problem 5.